Look at the bandwidth at the 10 GHz band with a millimeter wave frequency. Today I designed the millimeter wave antenna with have the point is that doesn't matter what kind of the software we use. We use the CST software, the structural in SSF or something, the different methods antenna. Now we create a template, the section, then the plane. The antenna has look like of structural, the planar, and we chose the time domain because we want to study antenna is divided and range of the frequency. Then the gigahertz, that's is okay. This is structure from 30 gigahertz up to 45 gigahertz monitoring edge far field over what the frequency is 35. Why 35 gigahertz? Because I know what that frequency is antenna is going to the resonate. The next, alright, then the modeling, we chose local WC as is kind of shown as a new coordinate here. I am viewing the just click on the work the plane. I just want to grid the mesh and the simulate the all the first we want to create the antenna subtract with the rectangular shape. In the modeling choose the rectangular, then the double click and double click the subtract. What is the 4.5 millimeter, so I put like the minus 2.3 divided by 2.35 divided by 2, and then it is a thickness of 0.9 millimeter equal to 3.5 millimeter. Then from here loud from the material library we go to the rotor. The antenna subtract is the rotor 0R04450. This is one. Rotors are the 4450p, so we ellipse of 3.3. okay, all right, then the click. So then we go the back side. We want to see the antenna ground. I just press B, then the subtract select S by pressing the keyboard, double click on the just click, then the go the weak section, and then the antenna has rectangular ground. White of the ground is the same as the white of the subtract, and it goes until the W max of 1.6 millimeter. So then for the thickness of the ground is just a thickness of the copper coating. I can find it the database sheet of the subtract. Actually the thickness of the I'm going to using this kind of subtract is a standard thickness of for this subtract. I can find the all of the companies, so that is T. I just name is the minus 3. Then it's I just minus 3 is 0.1.257. all right, the material of course is copper. What is the copper? That's 1, and okay, then I press D. The antenna is the feed by a microstrip line. So far I am going to select 1, and then it has a kind of the rectangular shape microstrip line. The line has weighted of 0.18 millimeter, so the minus 0.18 divided by 2, 0.5, 0.18 0.9, thickness of 2, the plus T. And because it is a copper and the W max of 3.315, so it's also copper, so it's okay. And then I'm gonna choose the cylinder one, double click and double click and double click. Then we chose the cylindrical direction because it's going to place the subtract outer radius is equal to 0.3 millimeter, inner radius 0, then the cylinder height is equal to 4 millimeter. The consider one cylinder's height should be subtract the thickness, so it's is 0.09. It started from 0.09 and it goes up to 0.09 plus 0.4, and then the U center okay 0.5. then the direction of the micro S3F feeds this line, the direction is goes to 3.05. the material is we got the roser, it's roser I think is 5880. let me find 8580 fit the ellipse of 1.9. it's okay, and I'm going to select the surface by pressing S, double click on it. I want to put a copper plastic element on the top of it, so the copper, I'm gonna go to the coordination thickness is equal to the copper, which is the considered as a T, and the material is copper. And then I need for the also the just find press control and click this, the double click gonna right select it right on the click them, and then transform I chose a copy, and then I chose the transfer right just here. Hold on. So again I'm not going to close them, and then and the transform, and if I copy this time as a 4 time, let's get down zero point 0.08. okay, right now we are going to define, we have the guide the gonna exciting the antenna, so I just select the microscope fit line. We are gonna them to home the macros, we are gonna solve our ports, calculate port extension efficiency. In this section I'm gonna design, I have the compare the white of microstrip line, the substrates that I use, and close the right now. The most interesting section is the running the antenna. Alright, it is running without any errors, and let me see the bandwidth. Wow, look at the bandwidth of 10 gigahertz with bandwidth is a millimeters wave frequency. So it's gonna potential start from here up to here, so let's round for 31 gigahertz up to 41 gigahertz, and it has a resonance frequency around the 35 gigahertz, and with the more accuracy it is let me see it around 34.4 gigahertz. That's why the close the radiation pattern at the 35 gigahertz. Look at the minimum return loss, minimum 31 dB. That's very good. Then it's a far field I'm gonna show the how to antennas radiates the antenna radiation patterns at the 35 gigahertz. The antenna has kind of the radiation pattern. Look at me, the dipole antenna. So I can see it's a kind of it's cover all around the antenna. And if you show the structure, I can see the radiation goes like this. Gonna the show the imaging of the one's antenna. The radiation pattern goes the like a tube around its look around the dipole antenna. It's a direction like this. We look at the electric field, so we can see the wave is coming by this microstrip transmissions line and gonna excited this for positive element. So and these dielectrons here is kind of act like a delta resonator. So it is a reality depends on the technology that we have the can fabrications in the different methods. For example, I can print this one as a PCB layer and then can print this one as one and they use the glue that stick them together on the same as a ceramic ITC. There I can just print this layer by layer. Or the technology, if have the 3D printers, then can 3D print one top of the substrate, and then it should be the design that I didn't copy any